Okay, so to find omega, we also need the inertia, right? And we need to use the table 10.2 because those objects we have in the problem are not point particles, and if they were, then I would just simply use mr square. But they're not, so we need to figure out what they are and which inertia is the inertias are the cases for this problem. Remember that we have a rod and a disk, right? So the disk is rotating around its central axis, so I think it's pretty straightforward to choose this. Again, this L is much smaller, but inertia of the disk is 1/2 mr squared. For the rod, I kind of want to go back and then take a look at it carefully. So if you look at the figure, we have that height 1 meters and a thickness 2 meters. Okay, and so if we again go back, it's a bar, right? I don't really have a bar here. So there's a thin rod, and it's rotated around this like perpendicular axis to its central axis. And another one, the slab we have here is also rotated similar way. But which one is correct? So I'm not only given the length of the rod or the bar, I'm also given the thickness, right? And if you look at E, there's no such thing. It doesn't matter what the thickness is. So I'm gonna use this one for the rod that I have, or the bar that I have. So this is gonna be for the disc, and this is gonna be for the bar, okay? The reason for that is, again, I'm given A, although A is not as big as shown in here, much smaller compared to B, but I'm gonna use the length of the bar as B and the thickness as A. Okay, and I'm gonna use 1/12 m A squared plus B squared. So that's the plan. I hope that's clear because they're giving us a thickness, and if you choose this one here, that doesn't have any thickness related, so I'm not going to choose that one. Instead, I'm going to use the part I, which is for the slab. It's similar to the bar, okay? So now let's go down to get to that equation again. And so we did find out inertias. For the disk, we are using 1/2 mr squared. For the bar, we are using 1/12 m mass times a squared plus b squared. So you need to be consistent, be careful. Its labeling always helps. So disk inertia, disk's mass, and bar's inertia and bar's mass, and all their parameters consistently. So the disk, however, is not rotating from its center, right? So it's not simply rotating from this point, it's rotating from down here. So this is that distance, right? So we need to use the parallel axis theorem. Since it is rotation is not from the center, but it is around this point. Remember the parallel axis theorem? We need to add this mh squared to what we have for the center of mass for the disk. Okay, so from the table, what we get is the center of mass rotations. And for the bar, again, it's not rotating around this center, but it is rotating from this point. So this is going to be the h for the bar, and making sure that those two rotation axes are parallel, because the what we're applying is called parallel axis theorem. And it's from the equation sheet. It says the new inertia is the center of mass inertia from table 10.2 plus mh squared. Okay, so in this problem we need to use this parallel axis theorem for both of those objects. Okay, and that's what we're doing. We are finding those, and those h's are not the same. Okay, so be careful with that as well. So for the disk, we have the center of mass inertia, and we have that mh squared, and that is the parallel axis theorem. And for the bar, you can see it here, we have that center of mass and also the mh square. Center of mass, this is A, this is B, so like that was the thickness, that was the length. Also check the parameters, how we are plugging things in. So hopefully everything is clear now. We needed to apply the parallel axis theorem. The equation is given on the equation sheet, so please get comfortable with those and realize when you need to use it. If not, if you don't understand, if you have problems, please come to our Zoom meetings to get for help. Okay, so and if you plug the numbers in, what you're getting is disk to be 2.102 kilogram meter square and bar is 0.333 kilogram meter square. So why is the disk is much bigger than the bar? Doesn't make sense. So like kind of notice that. Doesn't make sense. What happened here? I think the easier way to answer this is, first of all, disk has 2 kilograms and the bar has 1 kilogram. And for the disk, considering the rotation axis, the rotation point, which is all the way down, right? I'm going to go back to the original problem. You see the pivot point. Disk is much farther away from the pivot point, so the distribution of mass is much farther. Remember that inertia will increase when you locate the mass at a farther location. So that's the reason the inertia of the disk is much bigger than the bars, right? But what you need in the problem is the total, because we did solve everything assuming that was a combined mass. So the inertia in the equation, and I want to kind of remind you the equation here. So yeah, we applied energy conservation, we used the I in there. That I is the total inertia. Okay, so this is the total. Now we know what it is. We needed to combine those two when we needed to apply parallel axis theorem, but we got what the total inertia is. All right, so just add these up. This is what you get. And again, the inertia has a unit of kilogram meters because it is mass r square. That's the form, but the coefficients will change depending on the shape and the rotation axis location. And finally, we plug into the formula previously developed, as I showed just before. Then you can solve for omega, and when you plug everything in, you get 6.41 radians per second. Also check the numbers. This comes from this equation here. Okay, you plug everything in. We solved for y's and I, and m and g are given. M is 3 kilograms, right? The total mass. So plug those in. You should be able to get the 6.41 radians per second. Double check the answer if you can confirm that. And the last thing is finding the v, and the linear velocity depends on how far the point is radially away from the center of rotation. Since in this case r is that 1 meters plus that 5 centimeters, it becomes 105 meters, right? Because we are focusing on point P from the rotation axis. And so you're going to use r to be 1.05, okay? And since you have that omega here, multiply that r and you can get the linear or tangential velocity. And it's very similar magnitude to the omega because r is almost 1, right? So you can also check if we met the expectations and the answers are agreeing with those estimations. And multiple physics principles were needed to solve this problem. This example clearly shows the importance of moment of inertia for rotation problems. It is not the mass that is important, but rather how the mass is distributed, the location of mass, okay, from the rotation axis. So this wasn't a very straightforward problem, right? And please take your time to really absorb everything because there's so much stuff. Not just we are applying energy conservation, so I'm really hoping that you are very good at applying energy conservation. Now also we need to think about rotational kinetic as well, and then solve for your unknowns, but then really understand what they mean For a combined system like this, you have to think about center of mass as we did in the gravitational potential, and the inertia in the rotational kinetic energy is also the combined inertia. So we had to use table 10 too, but what we got from there wasn't enough. We needed to apply also parallel axis theorem as we have it in this equation here, and we had to do it for both of them because it wasn't exactly matching with what we have on table 10 too, but we could have it was possible to use parallel axis theorem to get those inertias, and as we did. And yeah, the last thing was just finding the tangential velocity. So if they were giving you another point, I'm just gonna make this arbitrary point somewhere here, okay? So let's just say like this is a point Q. You can also find the velocity of this point Q, right? So we find out this V here for the last part, for part B. What about Q, the velocity at Q, the point Q? It's first of all, it's going to be less, right? Because when you get closer to the rotation axis, since the rotation is around this point, it's going to get smaller, and it depends on this distance. So we use that 1.05 meters. Now you would use this distance, whatever it is, and you can also use the same omega, because omega is the same. They are taking the same angular displacement at the same time, those points. Omega is the same then, and you just needed to use a different r to get the velocity and tangential velocity at that point. Okay, so it's really straightforward. I want you to also be able to see that.